Hello, y'all. Got Lee Berry Jr. back for some more physics, and I plan on continuing where I left off earlier. So last time we were looking at the uh, uh, simple harmonic motion example, and I was looking at it and had the breakthrough that I missed right there to get the um, generating function. So with these equations here, I guess I'm so used to uh, these things being derivatives of time, but I still have to uh, remind it that these are derivatives of something else. So all I needed to do was, and it actually is earlier than that. Yeah, I noticed that from the notes from class, uh, we're able to get the E before F. But let's see if I missed that and didn't get that. I guess it's just a guess. Um, it seems like it's just a guess for the generating that leads to the generating function. Let's see if there's something else I'm missing. So we have this. This is the kinetic energy. This is the potential energy. You recall I multiplied a few things to uh, the m over m to simplify that to a sum of squares. Once we got to a sum of squares, guessed canonical transformation these two. So that cancels. Plug that back in. We get h equals f squared p over 2m. So this is where the departure is coming at right here. So we chose this P and Q to simplify. We have to get what FP is to I can see what's going on here. So we pick or we guess the P and Q for transformations into big P and big Q. We pick it such that when we plug this into the equation here, it simplifies. So we can guess what we want to plug in for P and Q in terms of big P and big Q and plug that in to simplify. Then we use those two things to solve for FP. So contrary to what the book does, the professor did is step from right here, and from guessing these two things, we can do P over Q, which is MW cotangent Q. So P equals MWQ cotangent Q. And then from there, we can do P equals partial F1 over partial QI. I'll make this all in blue. So that means that uh, integral of P equals F1 equals integral of MWQ cotangent Q dq. So F1 equals M omega Q squared over 2 cotangent Q, even though I don't know what happens to the constant of integration. Right. But that means that just from, but again, it seems odd because that's just a guess. Hey, good morning, PV7667. Good to see you. Thanks for dropping a line. Trying to figure out this uh, generating function deal. It's starting to become clearer, but it's still not 100% clear. Like, for instance, what's the best way to guess these canonical transformations? I guess you just have to look at what you have and think, what can I put in for Q and P that makes this canonical and uh, cyclic? Seems like I'll be using a lot of sines and cosines. I don't know why my monitor blinks sometimes. Maybe I need to update my driver. I need an update. Historically, that's been a sign that I needed to update my driver, but I've been doing a lot of stuff with my video card, streaming. I have the pad going and all kind of stuff. So I may need to update my video driver or something. My monitor blinks every now and then, which is the same thing that happens in one of our classes in the when we not in well in the meeting room when we have our meetings for the stellar lab on Wednesday. Notice that monitor blinks too. Maybe it's a internet connection thing. I don't know. All right. But so now the only thing I need to do is figure out the shortcut to get the big P version. So that's the little p version. Notice that there's a FP here. Well, let's see. Okay, okay, it's starting to get clearer. So this is one way to get the F1 for little p. So I want to get the F1 for big P. I guess this is it for big P or for Q. Let me see here. So we need one for capital P. So little p is this one. Big P is the same thing with big Q as the derivative. So that means that integral of big P is integral of is F1 is integral of m omega q cotangent q d big Q and negative that here negative that. So in class, professor got seems like that's different. That'll give me a different F1. Did solve for Q, for big Q, or at least for little q. It's a little bit, we're getting a little bit more clear how this works. What I may do is try a totally different problem and see if I can get the full amount. But we should made a little bit more progress. So as long as we have the Hamiltonian, we want to simplify the argument in the Hamiltonian in relation to momentum, which is P, and the generalized coordinate, which is Q. In this case, the generalized coordinate is X, because remember this started from a simple harmonic motion mass on a spring. All we have to do is pick a guess canonical transformations P and Q that simplify this thing in terms of big P and big Q, and then use that and the fact that little p is equal to the partial derivative with respect to little q of the generating function, and capital P is equal to the negative derivative with respect to big Q of the generating function. And we could use integrals right there to get the generating function F1, right? So I'm going to have to try this with some different equations to confirm, but at this point it's seeming all right. So thanks for dropping a line, PV7667. Everybody else who popped in as well, make sure to like and subscribe if you haven't. This was just a small follow-up for what we did earlier. To see that right there, we could have gotten the generating equation right there. It looks like this should give me something similar, at least maybe a different form of the generating equation. It looks like the book went ahead and solved for Q and got big Q out of that. So there's several things you can do here. But she'll still be back. And if I'm not back later, I'll be back later in the week. We'll keep on going through this thing. So thank you all for watching. Thanks for those who dropped by, like and subscribe. I'll see you all next time.